Welcome everybody. I've got a few computer screens here in my home office, so hopefully everybody is in the same situation here and doing well. Today I'd like to give a little talk on some work that I did about 2 years ago, a year and a half ago. And yeah, I think it's kind of an interesting thing. It kind of opens up a world that you may not know of in terms of global monitoring for nuclear explosions. So I've got a few slides here I'd like to put up in a second. And if you're the first time to this platform here at Twitch, it's my first time as well. There's a kind of a chat. That's how you can communicate with me. And so I have that up on my screen here, and I can see questions that you have, and I can try to field these during the talk or after we have some time to even to go back and forth. But I can address them verbally if you send them in. I can try to type as well. I can't hear anything you're saying, but I think you'll be able to hear and see what I do here. And yeah, just to clarify on the chat here, my handle is David Barkley's handle, D Barkley. So don't get confused by which David you're talking to here. But yeah, thanks for inviting me to give this talk, and yeah, hopefully you enjoy what I have to show here. So let me move on to my slides. Okay, so if a submarine falls in the ocean, does anybody hear it? I really want to talk about how this missing Argentine submarine was found a year after it was lost through analysis of acoustic detections on a global sensor network. It kind of came, let's see here. Whoop, there we go. So maybe that title rings a bell here, but I remember hearing this as a young child. In a young child's mind, hearing a question as silly as this: if a tree falls in the forest and no one is around, does it make a sound? I would say, well, yes, it makes a sound, but I didn't quite appreciate what that question was trying to say. So maybe not, if we define sound as vibrations perceived by a human ear. But then you'd think, well, this question came about in the 1700s. Surely they didn't have ways to record sound remotely. So if we had a recording from a microphone in the forest and a tree falls, you could say that it made a sound. So maybe this question just doesn't really have the merit that it used to. But it really does hone in on the point of, if a sound is made and it's not heard or it's not perceived, how do you know that something had happened? So this kind of brings in a major point that I'd like to make here, that can sound perception be automated? Because there's no way that people can be around recording sound by hand all the time, writing down where sounds were made. And in fact, that is the goal of the network that was set up to enforce the Comprehensive Nuclear Test Ban Treaty. This network is an extensive multi-platform, multi-country effort that includes hydroacoustic monitoring, infrasound monitoring, seismic monitoring, and radionuclide monitoring, listening for the most grievous of environmental disasters, a nuclear test. This mechanism was set up by the UN, and countries are ratifying them slowly. A few of the large powers, nuclear powers, have ratified it, but there are still a few that are wary of this. Now, this is not a ban on nuclear weapons. It tries to promote non-proliferation, but the basic idea is that there's a ban on nuclear testing due primarily to the environmental disaster that each one of these tests puts on the world, a burden that we no longer need. So basically, through this mechanism, the Comprehensive Nuclear Test Ban Treaty Organization was set up in the Preparatory Commission, which is to make sure that all the pieces are in place to both monitor the world for unexplained nuclear explosions, and this is done through the International Monitoring System, or the IMS. And data from the 4 types of monitoring systems are piped in to the International Data Center, which is held in Vienna. And there's a processing mechanism there that automatically processes the data, finds correlations between different detections, seismic or hydroacoustic detections, and then it provides an automated bulletin, which is then revised and analyzed by a human analyst to make sure that the bulletin has correct associations. And this is something that an international data center provides to the countries as part of the treaty. And the main goal of this is that if there is an anomaly, an unexplained anomaly, that probably could be a nuclear explosion. Now, the goal of the organization is not to say there was a nuclear explosion, but that there may have been a nuclear explosion. They will then initiate, this is of course when the treaty goes into force, an on-site inspection. So people who sign, or countries who sign the treaty, are beholden to allowing on-site inspectors to come and investigate an area that should not exceed 1,000 square kilometers. No distance greater than 50 kilometers in any direction. So the mechanism is here, the on-site inspections. Now, we have had a few nuclear explosions from the DPRK, but those were not unadvertised. They were detected by the system, but there was no need to go show that there wasn't a nuclear explosion there, because they advertised that they were doing nuclear tests there. Also, North Korea is not part of the treaty. They have not ratified it, but there's always a potential to get everybody on board. So this international monitoring system consists of the four types of sensors. Here's a map of the different networks. Now, there are also many auxiliary networks that feed into this, seismic networks especially, that can actually boost the coverage of the detection of nuclear explosions. Now, I'm going to just primarily focus on the hydroacoustic stations here. And this is a hydroacoustic network consisting of 11 stations at 6 locations. Now, a station is a small, roughly 2 kilometer on a side area that is sensing continuously low frequency sound. Sampled at 250 hertz, it can detect sound at about 100 hertz before there's filtering that kind of rolls off any of that higher frequency noise. Now, I said 11 stations and you see 6 locations here. That's because these locations are at islands around the globe. And to make sure that you don't have sound that's blocked by that island, they put a station on either side. So there's 2 on each one of these islands, and then you see one off the coast of Australia there. And there's only 1 station there because they don't put one on the other side. The coverage for hearing a nuclear explosion is sufficient by having each ocean instrumented with enough that there won't be any sound blocked by any of the bathymetric features. And all of these are then a live satellite uplink to the International Data Center in Vienna, where the data is automatically processed and associations are made. So when we look at one of those locations, the 2 stations at around an island, typically they're set up in a southern and a northern triplet. And a triplet would be 3 hydrophones that are on about a 2 kilometer baseline. This gives the ability to actually get some resolution in the bearing or azimuth of incoming sound waves. And now these all are moored in quite deep water, about 200 kilometers from the actual island. So these islands steeply rise out of the ocean. They're in the deep ocean. And the hydrophones are suspended about mid-water into the SOFAR channel. And this actually provides the greatest coverage because the sound propagation is actually preferable in the SOFAR channel, where we have a minimum of sound speed. Now, this isn't the case for all the stations. Some of the stations are far enough south that there is no active SOFAR channel because the surface waters aren't warm enough to actually cause that increase in sound speed. So just want to give a few shout outs to why the SOFAR channel, or the sound fixing and ranging channel, has its name. And basically the principle under which the Comprehensive Nuclear Test Ban Treaty network can actually locate a sound to that precision, needing to be within roughly 50 kilometers. So back in World War II, there was a network developed, the SOFAR system, to detect pilots that had crashed into the ocean. And the basic idea is that if a pilot crashed in the ocean and we have no idea where he is, they could drop a small disk or a small charge that would sink down to the SOFAR channel, about 1,000 meters deep. And it would explode. And actually, the pilots would have a little chart there to set the charge based off where they crashed, so they know that they would get the explosion to be in the precise place that they needed, because it's a small little impulse. And this would propagate thousands of miles or hundreds of miles to different hydrophones located around the area where pilots could be. And the basic idea is that if you have a recording of this, and all these are wired to the same to the same clock, we could associate the arrival time at the two by the difference of the arrival time and find the location. Now, if you had two receptions, and these are two hydrophones that are quite a few distance from each other, and you know the source time, then you can know the location. There would be some ambiguity, is it to the left or to the right of the line. Now, if the source time wasn't known, which would be the case if a pilot crashed and there was no radio signal, it would fall somewhere along a line, but it would actually give you an ability to search along a line for a downed pilot. Now, even better, if you have a third reception, you actually could find the pinpoint precision of where that sound had happened. And so this was a way that pilots could be found, and perhaps now there's just better ways that we have satellites going around to find pilots, but it developed a very important system that you could locate based off precision timing an impulse origin in the ocean. So what the network's actually listening for is a nuclear explosion. Now, this is much larger than the small disks that were discharged by a pilot. We don't have any examples of an underwater explosion recorded on the network of this magnitude. But there was a number of tests, and I guess the only deep water test was Operation Wigwam that occurred in 1955. They put a bomb, a 30 kiloton warhead at 2,000 feet depth, about 500 miles off the coast of California. I have a little video of it here because I just find this fascinating. So the explosion here, you can see, was intense. And there actually were a number of underwater pressure vessels within close proximity to the explosion. I believe none of them actually recorded any viable data. But there were two networks, listening hydrophones, that were active, that recorded them near Hawaii and off the coast of California. And there's actually a nice paper here. I have a reference from Walter Monk and Zachariasen here, talking about all of the different reflections as the sound rattled around the ocean for hours and hours. And I know my colleague Brian Deshaw had looked to see, well, you can see here we have a really nice signal to noise ratio here. This is this time series of amplitude here at the bottom. And it's about 3-4 hours long. And you can see that it's not ending. So there must have been more and more hours of recording. But it was hard to find this data, and I think anybody comes up with it, that'd be a really neat piece to do, because you can see that there may be even multiple reflections. So this is sound that's rattling around the Pacific Ocean, reflecting off of seamounts, refracting, potentially even due to the oceanography, and maybe even going all the way around the world. So this is what the network's set up for, but it hasn't recorded anything yet, because the network is only about 20 years old. Hopefully it never does record a nuclear explosion. But what else does it hear while we're waiting for, hopefully, not the inevitable? And the example I'd like to follow here, which actually is something like a large impulse, it was the sound that was detected from the tragic descent of the Argentinian submarine, the ARA San Juan. So this happened in 2017 in November. And just give you a few tidbits of what happened here, and then go into my involvement in this project. But just after midnight on November 15th, midnight UTC, the submarine had radioed in and gave a heading and its speed and location, saying that there was some flooding in the battery compartment that caused a hydrogen buildup, and there was a fire. And that they were going to, in bad weather, which a submarine does not want to be on the surface in bad weather, was going to dive down to, I guess, periscope depth here, or 40 meters, and motor home northwards to the base. And then about 10 hours later, there was a iridium communication, which gave a fix to within about 10 kilometers of the submarine. And then nothing else was heard from the submarine after that. About 4 hours later, there was a sonic detection of an intense impulse on the CT-BT network. So this intense impulse is not a good sign for the submarine. It was probably suggestive of either explosion or some type of catastrophic implosion. Then a year later, and one day, the San Juan was found, first by sonar, and then the next day brought down some equipment to actually visualize with video cameras the San Juan resting at about 926 meters, much deeper than the submarine was able to submerge safely. So the search for the San Juan covered a very large area. And actually, initially after it was lost, for many months, a international search team was deployed using ROVs and even trying to dredge for this submarine based off of some last reported heading and a dead reckoning position. And so on the right here, I show a little map of the basic navigational aids that they had in defining their search. And you see that the orange line there would have been where they were going, and then they reported their new heading. And then we heard the sound, so based off the iridium fix and how fast the submarine was going, it should have been somewhere in that blue circle. Then roughly, I believe, 4 or 5 months after the incident, the search was called off. There was no success. They had scanned this whole area. It couldn't have been there. It was resumed about 10 months after his disappearance by the undersea search company, Ocean Infinity. And this is where I entered into this project. I had heard about this detection in the news. I'm always having my finger on the CTBT newscasts, but I hadn't done any analysis. But I had heard of this Ocean Infinity company in a fascination I have with the sound that happened at the same time that the missing Malaysian airplane, what is that now, 7 years ago, or 6 years ago, the CTBT put out a newscast that there was a sound in a certain direction, and it was at odds with the analysis that had preceded. So it never was included in the search area. And I had emailed the CEO of this Ocean Infinity company to consider before calling off your winner take all or no pay, no cost search effort to look in this area where the sound was generated. I never really heard anything back from Ocean Infinity on that, but then a few months later, they kind of cold called me because I guess they did get my report that I had sent them, and mentioned that they were looking for this the submarine and wanted me to look into confirming or validating the analysis that was done by the CTBTO, and also some of the other organizations, the British and the US, that had put in, I guess the French as well, had put in estimates of where the submarine was located. So I got into it and had a number of back and forth, and there was an active search going on, which it's always interesting trying to give people advice when they're spending money by the $1 million a day. And I got a lot of information from them. So this is actually a map here on the right of the search area that was defined. And there's area 1, 2, 3, 4, 5, priority areas. Let's search area 1. So I got brought in after all these areas had been searched because they were a little unsure of what we should do. Maybe the sound was made somewhere else. So I went into the analysis, and you can actually see here that the submarine was found there in area 1. It was just a very difficult place to look for something that is not meant to be found with sonar. And on the bottom left here, you can see kind of how the Ocean Infinity Seabed Explorer works. It has a series of side scan sonars that are put down to depth so they get better resolution. They have to get the sonar closer to the bottom to get the resolution they needed for detecting something this small. And so they did detect this submarine kind of in line with a ridge, and you can see that there's an impact crater here of where it hit the bottom. And now, as findings have come out, that the submarine it lost buoyancy, and then it sank deep enough where it was crushed. And it's the sound of the crushing of the hull of the submarine that was detected by the CTBT network. And here are those detections here. And the detections now were made at an amazing distance. The submarine did sink down quite far. Now, there actually isn't much of a, this is pretty far south here where the submarine was located. There isn't much of a SOFAR channel per se. And actually the water is not that deep that if there was a SOFAR channel, it probably would have been in deeper water. But because of the nature of reflections from the bottom and the surface, you actually do have a lot of trapping of sound that then gets coupled into the SOFAR channel as it goes north, or it gets coupled into the surface duct as it goes through the polar waters. So the sonic detections occurred on two of the locations: the Ascension Island station there in the mid latitudes in the Atlantic, and then the Crozet Islands station south of Africa there in the southern Indian Ocean. So the time series here, I have on the left side of your screen the same 25-minute window here, and you can see that the sound arrived at the station that was less far away first, and that's the upper plot there, and it has a nice peak there, very impulsive-like sound, and you also see then there's some other impulses which you actually can correlate based off of the characteristics of the signal to other paths that are coming in that are not along the geodesic or shortest path on the globe. Now, the southern station recorded a much more dispersed signal. You don't see the peak there. It's kind of almost like a packet of energy coming in over about a minute or 35 seconds. And there's a few other bits of impulses that you can kind of see in that time series on the lower left there. Now, those aren't necessarily from the submarine. They could be from ice falling in a different direction, and that's where the directional piece of the network actually comes into use. You can associate the direction of sound to was that sound from the same area. Now, the signal that's coming in there right around the same time as around 1500 actually is another signal that was going faster than the speed of sound in water. And there's been a lot of work done by the folks at CTBTO showing that actually is a ice coupled path, because it's occurred in November. There was a lot of sea ice there, and it had a propagation speed about twice the speed of sound in water. So it was able to actually skip past the arrival that was coming in through the water. It's a very interesting piece, and some potential there for actually doing some studies of what the ocean's made out of with such sonic signals. So one of the challenges in taking these signals at different stations and at different arrival times is how do you associate them to be the same signal? So we saw there that the one had a much larger peak than the polar path. And now when we look in a time frequency plot and looking at these two pictures, this is the same impulse created these recordings, both at 6,000 kilometers and 8,000 kilometers. They look very different, both in frequency and in the time dependence. You can see that there's kind of a peak coming in there at the Ascension Island station. That's what we saw in the data there. And the dispersion in the Crozet recording here actually has kind of a linear sweep-like signal going from about 3 to 15 hertz, and that sweep is actually something that we can predict by looking at the characteristics of the propagation. So I kind of want to give you some details there, because when you take a correlator and try to correlate two signals, these two signals would not correlate very well. So in terms of detecting the submarine, it actually did take a human to get into the loop, because the automated perception is only so good at finding signals at one station but not doing the localization based off of the multiple stations and the timing of them. So once these were identified and characterized as having been the same signal, then you can actually go back and start estimating to some uncertainty where that signal was generated. So to give some, I guess to give some explanation for why those two signals look so different, I'm going to talk about rays and modes here, some tools of the marine acoustician. So rays are, to me, a very natural way of describing the propagation of sound. It may seem a little bit a little bit confusing to someone who sees it for the first time, but they're basically a visualization of the path that like a packet of sound energy follows. And there's this is actually quite useful in radar and in light physics to do rays and image sources, and you can figure out where your reflection would be in the mirror. And in underwater acoustics, it's actually very important because there's a lot of refraction that goes because the sound speed is not constant, and that's what we were talking about earlier with the SOFAR channel. So you can actually build up some ray tracing algorithms on your own, or there's lots that are available. And what the idea is that you can find paths that connect a source and a receiver. And from those paths that connect there may be more than one based off how many reflections or bending refractions of the sound. You can actually build up a signal based off the timing of those. And that timing of the signal is going to be the integrated speed over the path, and that's going to give you a propagation time. And as we were looking at the propagation over these long ranges, there's an exaggerated scale here that kind of shows the water depth being it's probably 100-to-1 depth to range scale here. And you can see that the bending actually is occurring for these very, very shallow angle energy. And this is where the propagation of the energy is actually perpendicular to the gradients in the sound speed. And the sound speed in the Arctic profile there, it has kind of increases as you get deeper. And the equatorial profile has this SOFAR channel, this minimum at 1,000 meters. And the sound likes to bend towards the slowest speed. So in the Arctic profile, it gets caught in a duct. So the upper plot kind of shows that the sound is being reflected multiply by the surface and not interacting with the bottom. And likewise, in the equatorial profile, it's refracting both up and down and is trapped in the SOFAR channel. And this lets the sound travel very far without being scattered and actually maintain some element of coherency and energy as it goes thousands of kilometers. Now, we saw the ray picture there. You can actually cast that same picture in terms of the modes. And the modes are kind of describing which a set of rays that has a particular, it sweeps out a particular depth, and it has a particular speed, because the deeper rays in terms of the Arctic profile are going to go a little bit faster. They've gone through higher speed, higher sound speed water. So you can actually build up the propagation speed of the modes first by finding where's the energy of those rays concentrated, and then integrate the mode function, the depth dependent of the intensity integrate the sound speed over that mode function, and you actually can build up a propagation speed or group speed. And so now to look at that, that's kind of a one picture, and we know that there's going to be a path-dependent sound speed profile as we go over these thousands of kilometers. Here are the two paths here, and you can see that at different ranges along the paths. The San Juan location on the right, we kind of have that up on a slope, and then all the way to the island, it's propagating to the left, all the way to Ascension or Crozet. You can see that the sound speed profile is changing as you go through the different part of the ocean. As you get closer to Ascension, you're going through warmer and warmer water. We have a more exaggerated SOFAR channel. And as we go through Crozet, you can see it's going through the most southern part, kind of right around 2,000 to 4,000 kilometers from the station, and that's going to be where the speed is going to be the slowest because the water is going to be coldest there. And so we can actually take one of these modes, the first mode, which I always like using because it's the one that's going to be most persistent, and you can average the speed over the path, or integrate the speed over the path, and find what the propagation time would be of those modes. So if we do this now as a function of frequency, so this is, as we saw, those sound speed profiles were independent of frequency, but where the modes fit into, it depends on how long the wavelengths are. So you can fit more modes at higher frequencies into a waveguide, into the SOFAR channel or into that surface duct before it starts interacting with the bottom. And I say that it's important that we don't interact with the bottom for very long, because every interaction with the bottom will have some losses, either through scattering or through some attenuation in the fact that the bottom's not a perfect reflector. And as we march through and look at the group velocity integrated over the propagation path, we build up a propagation time. And you can see at the Ascension Island stations, the one on the left, we kind of have a group of modes coming in around the same time, independent of frequency. We also then, looking at the Crozet, because of that upward refracting profile and the lower frequencies, essentially mode 1 scanning deeper and deeper, faster and faster speeds, we have that linear dependence of the propagation speed. So going back to our signals here, we look at the SOFAR channel case, the Ascension Island, or the upward refracting Crozet on the right, and we draw a line there for what mode 1 would be. We can actually fit those propagation paths to that mode 1 structure. You actually see that there's energy coming in before, and that's the higher modes. So to give a little bit of a simplification on how the system works, the system actually does create some type of average group velocity, the automated system, based off of the environmental conditions. But a real good approximate for travel times, actually just taking the minimum of the sound speed. And this is good for deep water in the mid latitudes, where the minimum is going to be close to the bottom, or close to the SOFAR channel. Now it kind of breaks down a little bit if you go towards the poles, where the minimum's at the surface, and also where you start getting into the coastal shelf, where the water depth is a little less than, let's say, 2,000 meters deep. You start to get a real discrepancy, and this is actually difficult when you try to do the association as a function of frequency, because we really do need a frequency dependent estimate of what the propagation speed would be. So there is some power in associating the modal group velocity and looking at the frequency dependence and building up a propagation algorithm that can predict that dispersion for signal association. So just looking at the difference between the two estimates of group velocity or propagation speed, you see on the map to the right that the group velocity in the near shore coastal waters around Argentina is actually going to be overestimated for the minimum sound speed approach. That's because of the bottom reflections not being taken into account, and that increased length of the paths. And also it's going to be underestimated in the polar waters, where we actually are going to have some aspect of a deeper propagation where the speed's going to be faster. That's missed by the minimum sound speed approach. But for the most part, there can actually be a pretty much association, just taking a geodesic, taking the minimum sound speed profile from some type of global map of sound speed, oceanographic map, and associating the two. You can get some precision that actually just about meets the, if you have enough detections, meets the criteria for the treaty. Now, back to the search for the San Juan, the initial data that was put out by CTBT had only the 2 hydroacoustic stations. And that's actually, if we look here, now I have superimposed on that search map there, and underneath the bathymetry there, you can see the shelf there. It's on the left side. And the green ellipse is the air ellipse that was created by the arrival from the 2 stations. This is similar now to taking that 2-station detection for the triangulation. You'll see that it creates a line, and they're able to constrain this line based off of some propagation differences between or angular information from the stations. So there's a long extent there, over 250 kilometers. It's elongated like that because that is where the 2 stations lie relative to each other. Now, to improve that, we basically need a better estimate of the time that the signal occurred, because then we can actually get pretty much an unambiguous point. There, it could either be in spot A or spot B, but for these two, the intersection occurs only at one point here. And the auxiliary non-acoustic data actually was available here. Seismic detection, a seismic anomaly was detected on a land-based station about 150 kilometers north of the shoreline here. And this actually tightened the constraint of vent time, and the CTBTO was able to provide an air ellipse, the purple and the red and the cyan colored air ellipse there that were much tighter, and actually had the location of the submarine in there. Now this map was produced before the submarine was found, but remember it was right in that central box there. Also, in terms of trying to improve on the estimate here, a known source was actually deployed. And I actually have this documented in a paper in JASA from last year, and you can find that just under my name. And the source charge was detonated kind of roughly outside of the search area. You can see there it's annotated here on the upper right there. And the idea is that you could look at the propagation speeds from that and try to correct for some uncertainty. And there's some modifications here that were made. It didn't really reduce the air ellipse. So to say that was a well-calibrated experiment may be a bit of a stretch, but it did kind of prove the fact that these small sus charges actually can be recorded at 6,000 kilometers when they're far enough away, or I guess when they're in certain locations where the propagation is favorable. And then finally, what I had done is I actually looked at some of the non-geodesic paths to add a virtual station. A virtual station here, kind of the idea that if you look at what would be reflected in a mirror, you can actually figure out where that propagation would be as if it was behind the mirror. That's maybe a bit of a hard analogy to see right now, but let me just kind of show you what we had here to work with. There were many non-geodesic arrivals recorded at the Ascension island station. And here is a number of back azimuths from the automated system that comes out of the CTBTO processing. And I've overlaid that on top of this time series here, and you can see that there are 11 detections coming in, and they all have a very similar frequency characteristic of the implosion. And you can see things that look like they're coming off of the continental shelf, a reflection or refraction, bathymetric refraction as I'd call it, and even some reflections off islands, those lower paths at 10 to 9 coming in there about 13 minutes after the signal. So I focused on the most clear signal here, number 2 here, that one coming from the continental shelf, just north of the event. And what we could do here is we can actually build kind of the propagation path with an energy flux line or array, as long as they're not crossing as an equal depiction. And we know that the geodesics are good, sufficient representations of low frequency propagation in the ocean, because the scales here are much larger than any of the oceanographic features. So if you wanted to scan for warm coral eddies or something, you need to go to a higher frequency than 3 hertz. Or 10 hertz here is kind of where I've been focusing. But when you think about the refraction that's occurred by a slope, the multiple reflections as the sound energy propagates up slope, actually it's quite easy to depict these as a mode that is refracting on the slope. So here is just you take the phase speed that you calculate from the modes and build a map, and you propagate that through that environment. So this is a parabolic equation simulation here. And if you do that over a suite of frequencies, you can create a synthetic time series. So this is as if there was an impulse created every, I guess, every few minutes. You would have these wave fronts emanating out from a source. And you can see as these wave fronts propagate up the continental shelf here, so this is kind of a much smaller scale, about 500 kilometer on the side here, you can see that some of that energy is going up the slope and then onto the shelf, and some of that energy is being shed and refracted at a different angle off the slope. And so if I have a receiver now 5,000 kilometers to the northeast here, actually we'll be receiving that direct arrival and one of those refracted arrivals at a later time. So you can actually trace that back and form the streamline, the energy flux path, or you can actually take the back azimuth that was measured and shoot a beam onto the the continental slope there, and detect and get a path of energy that you can actually trace to a theoretical source. And so this is what I had done in terms of finding the timing of the submarine. I had worked this mechanics up and finished it after they had already found it. But my motivation here was just that they should not look in shallow water where refraction couldn't happen. So my focus here was that we should be able to do this, and now in the hindsight, looking at forming a 3-path virtual station model, you can actually triangulate the source and estimate the source time to a good precision. So here I'm putting candidate source times in and finding that the three contours of equal travel time intersect at one precise time. And that precise time was when the event happened and the location that it did happen. So I'd just like to, I guess, wrap up here. Take any questions after that, but I wanted to give a little bit of information on if you are interested in actually accessing the IMS database. And this is, I think, the hydroacoustic and the infrasound and the seismic stations you can all get fairly readily. It's harder to get the radionuclide information, and there's actually some very interesting climate research looking at the radionuclide natural composition in the atmosphere. There's a yearly fluctuation. Actually, there was some recent work presented in Vienna, I believe it was last summer, that it can actually detect climatic changes, like when the monsoon season is going to start. So there's actually some very interesting data. But because radionuclide data is very sensitive about, it's not just nuclear explosions that release them. There can be both the development of nuclear weapons and also hospital or nuclear reactor incidents that having some publication prematurely on the radionuclide data and undercutting potentially what the CTBT would want to emphasize their network should be used for could be detrimental to the goal of the CTBT. So I know that data is actually hard to get, but the other data is actually fairly easy to get in terms of things that are operated by the U.S. stations. You can get that through the IRIS Integrated Research Institutions for Seismology, which is actually hosted at University of Washington. And there's a very useful tool, IRIS Fetch MATLAB script that is built and it interfaces with the web. It's fairly easy to set up and it's freely available. And you can find the IMS stations under IM for International Miscellaneous. And they have Wake Island, there would be Diego Garcia and Ascension Island, and I believe the Australian station as well are all posted on there. Now, if you want to get the full 6 locations, you can get curated data with annotated data products or bulletins from the IDC with a 2-year kind of no-cost contract agreement with your research institution and the CTBTO. And this is available through their website, ctbto.org, and there's a virtual data exploitation center. And the basic idea is you put together a contract showing that you want to do this to help CTBTO achieve this. And it's just a fairly straightforward process. And it actually connects you then into the network of scientists doing research there. And the ideal way, and maybe it's actually a little bit easier for Canadian researchers, would be to go through your national data center to get essentially real-time access to the data. And this typically requires a government contract, but every national data center has their own rules. And essentially, if you're just wanting to get your feet wet into it and you're familiar with MATLAB, I highly suggest to go through the IRIS website and their MATLAB tools because that's the easiest way to get you onboarded. So that's all I'd like to talk about today, but I'm here on the chat here if anybody has any questions, and it was great to talk to everybody. So the question here being, is it possible to estimate the sub's crush depth with the received signals? Now, I think there's two approaches that could be taken. The idea that it was an implosion, a single implosion, and what we see in the signal is that there actually is like a repetitiveness to the signal. Now, when you have an explosion, there's an expansion and then a collapse and then a rebound of the air bubble that's created. It creates a bubble pulse. And the bubble pulse actually is very much related to what the ambient pressure was around and what the size of the charge was. A very predictable feature. So in the San Juan submarine signal, it's an implosion, and it's not to say that implosions can't have a bubble pulses, and I actually have measured implosions of light bulbs, and there is a bubble pulse. But the expansion is not necessarily there to create the retraction. That the piece that we see in the signal, that we do see a repetitiveness in frequency, but that could have also been from two pressure vessels collapsing at separate times. And there actually is some azimuth dependence, and there's some, Julian Vargas, a French researcher, gave a presentation actually at the annual or semi-annual conference for the CTBTO, and he showed that that one station has a little bit different of a difference frequency than the other station, and that probably suggests that there were two vessels that crushed. So from that, it's difficult to associate what the energy was of that, or did it all collapse at once? So I know that it hasn't been associated that way. Now, you could actually see in terms of the modal structure there, and actually back out what modes were excited and what their excitation was, and get a crush depth. But I have not done that yet, but it should be possible. There are no hydroacoustic stations in the north. Now, I think we know that there are stations in the north. I mean, I believe even David Barkley had a quote just I saw it in The Guardian the other week, that there was some analysis here on ambient noise sound from some Canadian arrays. Now, the treaty itself does not have a mechanism to integrate auxiliary data into their network, but they do, in terms of the analysts, go out and they bring in auxiliary data, and there is a clause there to allow auxiliary data. So there's a much interest in actually expanding the network with some of these research arrays that are out there. So although there are no stations part of the system, and the reason for that probably was political, and I understandably, with a 30 kiloton nuclear explosion, we'd hear these things around the globe. That there was no motivation to put one in the Arctic at the time, potentially because it was difficult, but I think there could have been other political reasons. So there's data in the Arctic. To get access to that data probably requires a connection to something like a national data center. Well, I guess if that's it for questions, we got one here. What kind of other signals could be received? Iceberg calving. Very much so. There's a number of interesting papers, and actually the CTBT is a pretty good, or CTBTO is a pretty good search term in looking for studies that have been done with this network. Laszlo Evers out of, I believe he's out of Oxford, had done a study, actually not just ice calving, but the iceberg scraping and following its path based off of kind of a continuous sound as a huge ice shelf with iceberg that had calved from the ice shelf had migrated northwards. One of the major things that's recorded on the network are seismic signals, or T phases. And I'm actually doing work to use these T phases to estimate what the propagation speed is from an absolute sense, instead of trying to look for error in propagation models based off oceanographic data. And I see lots of research on whale sounds that are recorded and population studies. And they're remote locations, so they actually are quite quiet typically. But I'd say ice calving is a constant sound in the Arctic stations from Cape Lewin and from the Crozet Islands. Well, thank you, everybody. And in terms of this last question here, thanks for the compliments and the applause, silent applause, remote applause. The status of the Malaysian airliner search. I've been in touch with the Ocean Infinity group, and I kind of have a line after this success here in finding the submarine with them. I think motivating them to go back out for it may take a leg here. I'm not exactly sure what the current times have put in terms of their operations. The method is robust. I think what I had actually found is that trying to calibrate the method, it's a little bit of a difficult situation when you look at the sound that was made back in 2014. That unfortunately, the day before the sound was made, one of the northern stations that would have been closest, this Diego Garcia Island, got shut down. The wire got snipped, or the wire got abraded by weather, and the only path that is recorded on that station is a refracted path. So there's some timing aspect there that adds some uncertainty, but an air ellipse of a few 100 kilometers square was created. So a search area is possible from there. I think motivating to get the ship out there will take probably some buy-in and maybe just a little bit more work. I think actually outsourcing this work to have other people look at it. It's a very small signal. This is not something like an explosion. It's a plunging of a aircraft into the surface, so that's not going to excite those modes, the energy propagation, like an explosion would at depth. And I think there's always some debate as to what the origin of that sound was, and there's a gamble there that that could have been something more natural, an undetected seismic event. But as I like to think, the hydroacoustics is so precise. That there was something made a sound there. So it's just kind of a coincidence, or is it worth investigating? It's a little bit different now in terms of just looking at the search for the submarine and how difficult it was. They passed over it multiple times looking for it. The submarine is meant to be invisible to sonar. So I think that the area that has been searched, there shouldn't be any doubt cast on that they had scanned that sufficiently. So I think that the idea that going back and looking in the same place would really disappoint me. But I think if anybody's interested in further email or something like that, I can send you some information. But looking at it yourself is actually pretty interesting. It's a pretty interesting piece of data, and available on the IRIS website. All right. Well, thanks, and everybody be safe. The actual prediction was within a kilometer after using the refracted path. Before it was found, it's always easier to go back and look at where it was. Before it was found, I hadn't built up the propagation model to the point of being able to create the path. So it was only more of a qualitative. And so I just kept them searching in the central area, and please don't go search in shallow water where there would be no refracted path. So that motivation kind of helped them look back into their original search area. But the more paths you add, just the tighter you can get. The CTBT estimate with the 2 hydroacoustic stations and the seismic was within 11 kilometers, and that's based off just the timing, not an actual arrival. And there's some coupling aspect there that I'm sure they could get. The offset of where they estimate it is based off of some delay of that sound getting coupled into the bottom. Either was it cratering that was a seismic detection that they detected, and not the actual implosion being coupled in. And I think that just based off of some of our research with implosive sources, they're much less likely to excite the sediment borne waves that would be coupled into the seismic waves. So likely there was a delay there between when the implosion happened and when the submarine cratered into the bottom. And how quickly can the method be applied? Right, I think in terms of building an efficient code, it's not that far-fetched, and that's kind of something I've been working on. But the code itself, in terms of running, it's less than a day to get everything up and running. So in the idea that you can get data in a day, but if you were to want to integrate this into an actual system, it could be done and processed in a matter of minutes. And I think that really building up a timetable could be a useful piece. That's how the CTBT works now. But then double checking your timetables with a propagation model, and then having a delay of only a few minutes, or potentially even it could be faster, especially using kind of the ray-based methods. All right, well, I guess I will end the stream there. And it was good talking to everybody, and I hope to see you maybe on the other side of the of the situation here, and or at a next virtual conference. And yeah, it's good to talk.